Good morning, professors and audience. I am Li Xianggao. My report is on the implementation of integral backstepping study mode control for quadrotor based on Pixhawk flight control board. And here is my outline. First, I will introduce the motivation for research of the quadrotor. And second is about its framework and dynamic model. And section 3 is about the controller design for quadrotor and its simulation. In section 4, we will run a real flight to verify its performance. Based on the testing result, the conclusion will be given in section 5. Recently, the increased application of automation control is becoming more and more evident. However, in the world of academic, most of our research focus only on simulation. For this reason, my motivation is on the issue of implementation, and my goal is to implement the integral backstepping study mode controller to a real quadrotor. For convenience, I will call this controller as IBSNC in abbreviation. Figure 1 is a typical quadrotor, which is composed of 4 motors. 2 diagonal motors are running in the same direction, while the other 2 are in the opposite. This is the battery, position module, and electric speed control. And this is flight control board, which is incorporated with altitude sensors. If the quadrotor becomes unbalanced, the motor's spinning velocity can be adjusted by the flight control board through its PWM signal. Our flight control board is called Pixhawk. It is a good tool for realization because of its compatibility with various types of vehicles. We set up the body frame and earth frame to describe the quadrotor behaviors. And note that the earth frame E denotes the coordinate in the earth frame. B denotes the coordinate in the body frame. And omega, composed of P, Q, and R, separated represented roll, pitch, and yaw angular rate rotating around the 3 axes of the body frame. By utilizing Newton formula and aerodynamic relations, we can obtain the translational and the altitude dynamics presented in equation 1 and 2. The relationship between the rotating torque, lifting force, and the motor angular speed are shown in equation 3. In this part, we will talk about the controller design method and its implementation procedure as described in figure 4. From simulations, firmware, virtual environment to real test flight, I will explain each stage clearly in the remaining PowerPoint slide. So let's begin from the controller design. The IBSNC is composed of backstepping and study mode controller as shown in figure 5. And for unordered systems in equation 4, use backstepping for the subsystem first to n-1 to set its desired state variables. For subsystem n, use study mode to design the controller to meet the desired state variables. We simulate 2 IBSNCs using MATLAB in a hierarchical thing of figure 6, and the outer loop is for for translational dynamics, and inner loop is for attitude. We also implement external disturbances to examine the robustness of a system. Figure 7 is a simulation of disturbances in torque and force, and each one consists of a constant and random noise. As you can see, the force disturbance happens before the 5th second, and the torque disturbance happens in 5 to 10 seconds. For 2-order nonlinear systems like translational and attitude controller dynamics, we define alpha 1, alpha 2, alpha 3 and alpha 4 to rewrite equation 5 and 6 into equation 7 and 8. For translational IPSMC, the input is precision tracing error, and the output is the desired attitude to attitude controller and the lifting force to the model. In backstepping, define the tracking error, then design the state variable as the virtual controller to make the subsystem and asymptotically stable. And after that, trace back to higher subsystem. So enter the staging mode. Define the tracking error as staging surface, then design controller to make the system state variables convert to the staging surface. And for attitude IPSMC is the same way. The input is attitude tracking error, and the output are torque that makes roll, pitch, and yaw. And we adopted IPSMC examples from the journal as shown for equation 9 to equation 12, and all of them could be verified by the Laplace theorem. After that, we set flight targets and simulate the flight that generates the trajectory in figure 8. It's just like a baseball player running from home through the base 1, 2, 3, then return back to home. In figure 9, we check the attitude of the simulated flight. As you can see, when target changes, the surge weight could quickly converge to desired attitude, and the error is limited on the effect of external disturbances. And figure 10 is the position of the simulated flight. As you can see, when target changes, the quadruple could quickly reach the target. Then we start to transplant the controller into Pixhawk, and we are using PX4 as firmware for Pixhawk. On each application layer, the controller runs from the user command down to the motor spin. And its data relies on the data mining process using its sensor devices. The PID is original control method in Pixhawk for both translational and attitude controller, and we revised the translational part. To collaborate with the real situations, the controlling output must have the limitation to meet the motor's constraint. And after that, it merged with the direction angle to convert to quaternion. These two steps are different from the simulation, and our job is to implement the IPSMC to replace the original part of PID controller. So the IPSMC is implemented using the Qt creator, then GCC compiled it, burned into a Pixhawk. And we use the JMS sim as our virtual environment to examine its performance. As it turned out, let me show you to everyone. So at the beginning is the console interface. I click the command. So I open the JMS sim. It's the virtual environment I use. Then it's a ground control station. I open it and I set 3 targets to form a triangle. And this is a parameter in the virtual environment. Then I open it, and the quadruple start taking off. We set it to 20 meters high. The virtual environment is used to examine our performance of the firmware. So it could safely reach to target 2, then change the direction to target 3. Then return to the starting point. After that, it could safely landing off to the ground. Okay. In the stage of the real flight test, for the restricted area reason, we went to National Central University to test our quadrotor. And let me demo to everyone. At the beginning, the quadrotor takes off from the ground to 5 meters high, and they headed to base 1. We got 2 persons standing on home base and base 2. So as you can see, when the quadrotor left from home, the camera switched to the side of base 2. And when it came back, the camera also switched back. So you safely touch it to the ground. So we download the data from the flight report. As you can see in the bottom diagram, when target changes, the quadrotor will rotate its directions to meet its desired the desired one. And judging from the X and Y diagram, the real trajectory is just a little phase lag from the setting one. In conclusion, our experiment shows that the performance of IBM SFC could be verified in a real flight. It's such a pity that we have not enough time to implement IBM SFC in the attitude part of PS4. So in the near future, we will keep pushing it and looking forward to apply it in air delivery service. Thank you for your attention.